turned out to be a tiny handful of powerful genes.
So what this means is in some ways, some sense, evolution is a simpler process than we first thought. When you think about all of the diversity of forms out there, we first believed that this would involve all sorts of novel creations, starting from scratch, again and again and again. We now understand that no, that evolution works with packets of information and uses them in new and different ways and new and different combinations without necessarily having to invent anything fundamentally new, but new combinations.
Suddenly, the commonality of form among animals was understood. Animals resembled each other because they all used the same set of genes to build their bodies. A set of genes inherited from a common ancestor that lived long ago.
And what we see now among all the animals are just variations on a body plan that existed 500 million years ago.
And there's only one inescapable conclusion you can draw from that, which is if all of these branches have these genes, then you have to go to the base of that, which is the last common ancestor of all animals, and you deduce it must have had these genes. So the whole radiation of animals, the whole spring of animal diversity has been fed by essentially the same set of genes.
Ed Lewis shared the Nobel Prize in 1995 for the discovery of the universal set of genes that builds the bodies of animals.
And so, yes, it came as a huge surprise, not only to people like my mother, who says, my God, an earthworm and a mouse, an earthworm and me, share things in common, but it came as a surprise to other scientists that there was this profound conservation of mechanism, of building embryos among all these different kinds of animals.
What about us? Our bodies are built from the same genes that build all other animals. Yet, we are different. No other animal designs or creates like we do. We seem so special. It's hard not to think that we're somehow an exception to evolution. But of course, we're not. The transformation that led to us was no different from other transformations. Our crucial turning point seems to have occurred when our ancestors left the trees and began to walk on two legs.
We don't know exactly when or even where our ancestors became upright and bipedal. We think it goes back well over 4 million years when these ancestors came out of the trees and began to exploit food sources on the ground in terrestrial habitats. One of the key elements that would have been so useful to them would have been freeing their forelimbs, their hands, to be able to gather and carry foodstuffs over long distances. Once that happened, it opened up an extraordinary breadth of possibilities and opportunities.
Most bipedal hominids went extinct. But one branch went on to evolve larger brains. That branch eventually led to modern humans. So how did this crucial transition to two-legged walking begin? Liza Shapiro of the University of Texas looks for clues in living primates.
When you look at the fossil record, all you have really is a pile of bones. It's a non-moving entity. There's not much you can know about it unless you look for living analogs. So if you look at living animals, you've got the bones, but you can also look at how they're moving.
In their movements, living lemurs resemble tree-dwelling primates that lived up to 50 million years ago. We didn't evolve from lemurs, but they may be the best living analog for those distant ancestors.
When we're trying to reconstruct a scenario about how humans evolved bipedally from this ancestor, we have to know what it was we started from if we're going to come up with an explanation for not only how we made that transition, but why.
Today, Shapiro was gathering data on the movement style of a lemur. Small reflectors have been gently placed on the animal's back. An array of infrared cameras will record the lemur as it walks across this makeshift bridge. Of course, getting a lemur to do just about anything on cue takes a bit of doing.
There you go. Leap up this time.
Finally, the animal makes it across.
There you go. Oh, good.
All right. Got that.
And he's down.
The motion of the lemur's spine can now be analyzed in 3 dimensions. The data reveal that lemur spines are extremely flexible, capable of many kinds of movements.
Lemurs walk quadrupedally, but they're also very good at leaping.
Like these lemurs, the early primates probably moved in all sorts of ways. Down on all fours, scampering up trees, even leaping in an upright position. They weren't limited to just one style of movement, so they could serve as the starting point for a number of evolutionary experiments. And most likely, that's just what happened. We weren't the only ones to evolve from those early ancestors. So did most of today's living primates. Our closest living relative is the chimpanzee.
Stand up.
We didn't evolve
nice.
from chimps, but we do share a recent common ancestor.
Can you walk over here?
That's why our DNA is nearly identical to theirs. And why our skeletons have the same number of bones arranged in nearly the same way. But the few physical differences that set us apart seem to have made a great difference. Chimps don't walk on 2 feet.
Jewel.
They've evolved a different style of getting around called knuckle walking.
Knuckle walking is a very specialized adaptation that we see among chimps and gorillas today. It's an adaptation to walking on the ground.
Knuckle walking was as valid an evolutionary experiment as 2-legged walking. But the difference in our walking styles, which may have affected our intellects, is seen in the few slight differences in our skeletons.
Here are 2 skeletons of modern primates. This skeleton I'm sure you all recognize because it's a skeleton like yours and mine. This is a modern human. But this smaller skeleton is one of our closest living relatives, the chimpanzee. We began walking on 2 legs, and that made a whole series of modifications in the skeleton. In humans, the spinal cord comes out of the base of the skull and points straight downwards, rather than coming out of the back of the skull. The pelvis is shaped very differently. A chimpanzee has a long, narrow pelvis. Ours is short and squat. We walk with our knees close together. Chimpanzees walk with their knees wide apart. These are minor differences. These are the sorts of tinkering that evolution did to change us into a modern biped.
What if our ancestors hadn't stood up?